everyone to the last lesson of this Laboratory of Cloud Computing course. This is the last lesson, and as promised, I will dedicate this last lesson to one spatial argument, which is not very based on coding and programming techniques. We are going to talk about AWS, Amazon service, and in particular, we are going to talk about Lambda. So let me share my computer screen in order for you to see what I'm seeing. Okay, now you should be seeing my desktop, and with wait, someone asking probably for. Okay, you should be seeing perfect. Now let's start with. Let me find the diagram I've found. Okay, so let me start with where is it? Where is it? No. Here. Okay. So what is AWS? AWS is a service that Amazon provides for implementing and deploying web applications in a cloud way, which means that we're gonna perform. The service allows the programmer to write stateless and RESTful pieces of code that we called lambdas or lambda functions, and these pieces of stateless functions are basically an implementation of they are basically an implementation of the functional approach. I'm sorry, I have to interrupt you because there is someone knocking at my door. Excuse me. I'm here. I'm sorry, there was someone knocking at the door. We were talking about what is Lambda. Lambda is the way how you implement these stateless entities. This is something very deep, actually. As you probably know from the world of functional programming, lambdas the term lambda comes from there. The term lambda in computer science literature and in language literature means an anonymous function. And of course, this term is used by functional languages for representing anonymous functions. Amazon reused this term for representing their own interpretation of what is an anonymous function. It has something to do with the original lambdas from the functional world, but it is only as slight equivalence. In the sense of AWS lambdas, we're talking about stateless pieces of non-functional code that must behave as if they were functional. What do I mean? I will show you a quick example on Visual Studio Code Editor, which is this. This is JavaScript code, as you can probably recognize it. And what does this code do? We will explore the code in half an hour or so later in this lesson. But basically, what this code do is to provide a way for resizing an image, a picture. We will see the details later, but the concept is you do not have to implement a Lambda in a functional way. Not necessarily, because the language you can use for implementing it is a normal imperative language like JavaScript, for example, or C# or Java or other languages, or Python, which are normal imperative languages. The point is not lambdas in the sense of lambda functions within the language. The point is that the overall code needs to be stateless. So the overall algorithm that you have to encapsulate within this procedure must be an algorithm that picks some input arguments, does some processing, and returns some result without any side effect. That's the point. You can have side effects within, I mean, local side effects within. That's why I'm saying it is not truly functional programming. It is not pure programming, but the overall container is like a function. It means that it doesn't side effect the global context. It only has arguments, can assess some data, produces an output, and returns the output. Why is this architecture in this way? Look at this diagram, for example. This is a diagram of how the Amazon overall AWS architecture work. And as you can see, the AWS Lambda is here where I have my mouse pointer at the moment. And with that component, you plug in code that performs some computation in a stateless way. Why stateless? Because it must be repeatable, reproducible. It can be ported from one machine to another. It could be, for example, executed in parallel if there are 1,000 connections from users, for example, and 1,000 users simultaneously ask for the same procedure, for example, resizing an image, for example. Well, there must be an infrastructure that allows this algorithm to run in multiple concurrent instances. And you are probably experienced enough as computer scientists to know that when you introduce concurrency in your program, you have a lot of problems with side effects. Because every time you modify some data structure, you need to protect it by means of mutexes or other tools for synchronizing data structures. You need synchronization. You need a lot of overhead code for dealing with the modifications in order to make simultaneous threads to not disturb one each other. So the reason why Amazon chose something coming from the functional world is this. They want you not to program in a functional way, but to provide your service in a functional way, which means that your service is seen as a function that only picks arguments and returns a result. In this way, they can instantiate 1 million, for example, executors of the same Lambda function for performing concurrently 1 million image resizing, for example, or whatever you are going to do. If there were side effects inside, you would have to introduce a lot of complexity within your algorithm for supporting multi-threading. In this way, there is no need to do that, because your algorithm is only based on the data that you receive from the input, and you cannot in any way assess data whose scope is in the memory of another thread. So it is a way for cleaning up the flavor of the algorithm and allow the programmer to write it in a simple way in order to be reproducible, instantiable in multiple instances, etc., and executed concurrently. So this diagram shows us basically how the overall high-level architecture of an Amazon AWS-based application works. There's the web browser, of course, and the web browser goes through this thing that they call Amazon API Gateway before performing and executing the Lambda. As you can see, there is also 3 other actors: Amazon S3, Amazon Cognito user pool, and as Amazon DynamoDB. Well, Amazon DynamoDB is probably very easy to understand what it is. It is a database, of course. So it has its own API, its way of working, and it is a plain database that you can access from within your Lambda code. Then there is the Amazon Cognito user pool. What is Amazon Cognito? Amazon Cognito is a name for the authentication service of Amazon AWS. Since we're talking about a service that runs only on the web, of course there are security problems. And Amazon wrapped the whole thing within an authentication box, and they gave this authentication subsystem a name, and the name is Cognito. And then there is Amazon S3. What is S3? S3 is the name that Amazon uses for the concept of bucket. Do you know what a bucket is? Bucket with the bucket, secchio in Italian. What is a bucket in this context? A bucket is a small memory where you can put temporary objects, and by objects I mean data, either real objects in the language sense, or simply objects in the sense of items, of data that you put in this bucket in order to be retrieved later. So it is basically a volatile file system virtualized on your code. If you perform intermediate computations, or if you have to save intermediate data, temporary data, stuff like that, you can use the S3 bucket. All these things I'm mentioning are not real things. They are APIs, basically. So they gave names to big groups of APIs. You have an API for accessing the S3 bucket. You have an API for accessing the Cognito, which means you have an API for authentication, and then you have an API for accessing the DB, the database. You might wonder what is the difference between the S3 bucket and the DynamoDB. The difference is subtle. The database, and it is a Dynamo database, which is a special kind of database. The database is a persistent memory model. The S3 bucket is a volatile memory model. So you see the difference. The database in this context has the same value of a database in normal application contexts. That is, my program performs some computation while the program is up, while the process is up, and some of them must be stored somewhere in order to persist them throughout the life of the process. This is a normal problem of computer science, of informatics. When you program, you have a language that expresses memory through bindings of variables to objects, for example, in an object-oriented imperative language. But actually, when the program ends, we are all used to know that when the program ends, the memory goes away. So we are very accustomed to a volatile memory model. That's why they invented the database in the first place in the 60s, in order to make programs able to persist their data somewhere in a place where that data is not lost when the program ends, when the process is over, or when the computer is turned off. That's the reason of databases overall. And in Amazon, in this AWS system, they separated the two things as we are very accustomed to understand. The database persists information. The S3 bucket is like a volatile heap memory. So what is the Amazon Gateway then? The Amazon Gateway is just a name, Amazon API Gateway, it is a name for working with lambdas and in general with RESTful APIs for the AWS system. So Amazon API Gateway is just a logic name somehow. It is nothing real. It is just a collection of things, of services for creating, publishing, maintaining, monitoring, and securing APIs at any scale, like the first sentence says. What does it mean at any scale? It means that it is implemented in a generic way, but depending on the size of your data, on the size of your algorithm, on the CPU time that your algorithm requires, depending on a number of performance factors, this system automatically scales into lower level system or higher level system for ensuring you the correct performance. And this is transparent to the programmer. You don't even know that. You just have a general way for doing everything. And for everything, I mean, either for summing two natural numbers, which is a very basic operation, to processing a whole record of 1 terabyte of data. You have the same system. And its internal implementation scales down automatically. Down or up, actually. So in order to understand how to create an AWS Lambda, we first have to understand what is an API. What is an API? An API is a general name. It is a general name that stands for Application Programmer Interface. API is a name that existed even before the web services and even before HTTP was invented. Then API is a term that you can apply not only to HTTP APIs, but you can apply the name even to libraries. A library, for example, a library in any language is basically an API. An API is something that exposes a collection of functions and procedures that the programmer can use to perform some computation or some task. Then the term API changed over the years. And nowadays, the term API means something more subtle. API means the interface that a program or an application provides to external programmers in order to use the services of that application. Let me make an example. For example, if you have an application like a desktop application, let's say, for example, Visual Studio Code, which is an editor for the desktop environment. Visual Studio Code is a program. It is not a web program. It is a normal program running on the desktop operating system, and it has an API. What is the API for? It has an API in terms of a collection of signatures of functions that allows external programmers to use Visual Studio Code in a programmatic way. So Visual Studio Code is an editor, so the user can use it through the use of the mouse and the keyboard, of course, no? But what if I want to write a program that uses Visual Studio Code for example, showing some text or editing some text? I repeat, what do I have to do for writing a program myself that uses Visual Studio Code? I need Visual Studio Code to expose an API to me in order for me, as a programmer, in order for me to develop a program that calls its APIs and makes Visual Studio Code perform something for me. This is the meaning of the API nowadays. Then what it is an HTTP API and what it is a REST API, this is even yet another meaning. This has yet another meaning. HTTP is the application layer of the iOS OSI stack, as you already know, which is the highest level, level 7 of the stack, and it is the highest level. So the highest level, like HTTP, provides an API to programmers. What is the API of HTTP? Do you know that? It is very famous. What is the interface that HTTP exposes to programmers for using HTTP? Do you know that? You should. It is very, very easy. I'm sure that you know that. Perhaps you didn't understand the question, but I'm sure that you know that. You want to try to answer? Let me see if someone... Get post, exactly. Lorenzo Boccalone just said get post, exactly. Get, and the third, they are actually more than 3. Did you know? Actually, the HTTP API has a lot of command, or a lot of patch, exactly. Then there is delete, update. Yes, basically there is also connect. But most clients and server implements only the post, the get, and the put at most. But actually, the HTTP protocol exposes 7 or 8 commands. These commands is the API of HTTP. And through HTTP, you can design a web-based HTTP-based API, and do you know what I'm talking about now? I'm not talking about the HTTP itself anymore. I'm talking about how, using HTTP, you can, for example, provide an API for web clients. For example, through using get and post with arguments on the URL, for example. So that's a custom API for web clients that uses the HTTP API for expressing itself. And what it is, a REST API. A REST API is something even different. You do not have to mistake and to confuse an HTTP API with a REST API. They are 2 different things. And in this diagram, you see the differences actually from the AWS point of view. But basically, what REST means is that you have to design a stateless API. Does it mean that a REST API always relies upon HTTP? No. You could develop a REST API even over FTP if you want to, or even over Telnet if you want to. FTP and Telnet are two different level 7 application layer alternatives to HTTP. HTTP is the level that browsers use, but there are also FTP clients that have their own commands, or Telnet clients that have their own commands at the level 7. And you could design a REST API even for those, not necessarily for HTTP. Because the REST philosophy is not being HTTP or not. The REST philosophy is to design an API for clients based on the web, of course, but the true core is stateless. Is that the API must provide a stateless API. So you see that in the web development world is turning, is converting, is going in the direction of stateless. Why? The web actually has always been stateless, because an URL and a web page is intrinsically stateless, because the browser does not have side effects, because every time that you perform a connection to some URL, the connection is stateless. You perform a get, you get the page, and that's it. If you go to another part of the web program, you simply have a different URL. You know that already. But over the years, programming in complex systems in a stateless way was a real challenge. And so people invented huge frameworks for introducing statefulness, that is side effects, modifications of the state of objects and of memory, to introduce statefulness into the stateless mechanism of the web. So the web has always been stateless, but the frameworks that historically have been developed in the last 20 years are complex machinery for creating the illusion of statefulness with a stateless underlying device like the HTTP web. Now, in 2017, kind of in the last 3, 4, 5 years, there's a reverse tendency, because people started to realize that statefulness is problematic, and the stateless paradigm is has more scalability and maintainability, for the same reasons why Amazon AWS formulated all procedures in the form of Lambda functions. For the same reason, because everybody realized that performing stateless computation is easier to implement on a server side. Also, it is cleaner from a client side. But this requires a rethinking of some algorithms and a rethinking of many habits from the programmers, because programmers are used to modify variables, are used to changes in code, are used to modify memory, are used to assign and reassign variables. So it is an overall community of millions of programmers that started with the stateless web, then went through the stateful web, and now came back to the stateless web again with a new mind. And the new mind allows an enormous improvement in terms of performance. So let me show you another interesting comparison. I don't know if you have ever heard of SOAP, S-O-A-P, like sapone, in Italian, sorry. And what is SOAP? SOAP is an older way for representing APIs through HTTP. So SOAP is actually based on HTTP, while REST is generic. Anyway, they are mostly used for the same things. What are the differences? There are many differences, and one difference above all the other is statefulness for SOAP. SOAP is older, and SOAP has been designed by its authors with statefulness in mind, because SOAP started to exist in the late 90s, where the web has just begun, and everybody wanted to make the web stateful, not stateless. So SOAP was born in those days, and today it is still used, but it has a stateful philosophy. REST is newer. Actually, it is interesting to know that REST is not so new. You might already know, I'm giving you a link. I'm giving you this link if you want to read something that is not very useful from a programmer's perspective, but it is very interesting from an historical perspective. What is this site? I give you the link here in the chat. What is this web page? This web page, as you can see, is the PhD dissertation, the PhD discussion of Roy Thomas Fielding, and the date is the year 2000. So it has 20 years after all. It is not so new. And who is Roy Thomas Fielding? Roy Thomas Fielding is the inventor of REST. And what did he invent exactly? He invented a philosophy of programming. REST is not a technology. REST is not even a protocol like HTTP. REST is a methodology, a philosophy in programming. So it is a guideline for designing APIs and services in a client-server fashion with stateless computations in mind. This is what he invented. And it is a style, if you want. It is not really a technology. And it is interesting to read because you see how few things changed in 20 years. Because 20 years ago, this guy invented something that actually already existed and was even older, but he translated it into the web thing, which was new 20 years ago. The web was new, not the concept of performing stateless computation. He designed a methodology based on a clean development philosophy, and he applied it to the web, which was something new. It is an interesting reading. Now, I'm not gonna tell you more details of SOAP versus REST. It is not the purpose of this course. We have only one last lesson, and of course, I'm not gonna show you code or technologies. I'm just gonna show you the overall thing. So just for you to know, SOAP still exists. SOAP is still maintained. SOAP somehow is an alternative to REST. SOAP is a methodology and not a technology, and it is based on HTTP only, while REST is more general, but they are both two philosophies. They are not two technologies. Also, SOAP has other limitations, kind of, from a security point of view, and from the formats for the serialization of data and objects. Serialization of data, excuse me, when I say data or when I say objects, I mean the same thing, because objects are data, okay? The serialization of objects or data is a very important topic in a client-server distributed application. As I already told you in the past 2 lessons, serialization is a huge problem. When you have an application running in 2 different computers, or in 2 different platforms, or in 2 different spots, you just need to serialize data that for communicating it from one to the other. And to serialize means to transform your data from your memory into a string representation that can be revertible and can be turned back to the original data structure. There exist a number of possible meta-languages for expressing any kind of data, and these meta-languages are often used as target languages for serialized data. XML is one, JSON is another one. SOAP only supports XML automatically, while REST supports also HTML, JSON, and YAML, which are different syntaxes, basically, for expressing data and objects. So REST is newer and supports newer stuff. But basically, they serve they have the same meaning, more or less. Also, SOAP is very used in enterprises and in critical applications. What are critical applications? For example, banks, banche, finance, money, and the movements of money, transfers of money, stuff like this, where there is money involved, there is also security involved, and it is a delicate thing to deal with money and to deal with transactions of money. And SOAP has somehow a reputation in that field, and the people use that mostly in those fields, while the rest is more used for all the remaining stuff. I'm not saying that REST is insecure, or I'm not saying that REST cannot be using for transactions of money. Of course not. You can use REST for anything, as you can use SOAP for anything. I'm just talking about what these 2 different methodologies created as a niche for themselves. Cioè, insomma, sono 2 nicchie, occupano 2 nicchie diverse, fondamentalmente, ma entrambi fanno entrambe le cose. Then, no, let me show you this. This is another interesting, I collected a number of links, and I'm going to share you that at the end of this lesson. I'm showing you and explaining to you, and then at the end of the lesson, I'm going to share all these links with you. This is another interesting thing to read. HTTP is not REST necessarily, but as you know, as I told you already, these are the commands, the whole list of commands for HTTP, by the way. And this is an interesting reading for understanding the asymmetry there is between REST and HTTP. What basically HTTP allows you to do is to implement the CRUDs. You know what they are? CRD, this word. These are create, read, update, delete. They are the 4 basic primitives for accessing any storage abstract machine, for example, a database. And HTTP allows you to use the web server in terms of CRUDs, while REST is stateless, and so the update function is missing. Let's talk now a little more about Lambda in particular. In this diagram, you see very roughly how an AWS account works in terms of interaction between the components. An account owner is basically a user that can execute AWS Lambda entities, which are functions, basically, on the remote side. By the way, everything I'm talking about today runs on the server side. As you probably already know, AWS as an overall system, as a big system, is actually all server-based. I mean, the computations are performed on the server. The clients only displays the results. This must be clear since the beginning. And look at the interaction between the user and the S3 bucket. These are the buckets. So S3 is like a temporary memory where you can put temporary documents or temporary objects or even temporary raw data. Then the Lambda function, which has its own access policy, which means it has its own security measures. The Lambda function is executed in the virtual remote environment, and the Lambda function can access the S3 bucket as much time as he wants to. It is a little complicated to recreate a working example of AWS Lambda. I did not install all the necessary technology on my computer for showing you the real thing, because it's complicated. You need compilers, interpreters that I don't have in this computer. Also, as you know, when you surely know, when you start even the most simple test, you spend 1 day for making things work. So it is not an ideal thing to show you in a short lesson like this one is. But I want to show you web pages where you can see how the thing works somehow. This code, by the way, is the same code that is here, and we can have a look at it. Look, this is an example of Lambda item. I repeat, do not confuse Lambda as a language construct with AWS Lambda. They have something in common, of course, the philosophy is the same, but we're talking, there are two different things. In JavaScript, you can implement an AWS Lambda entity, procedure or function, in this way. That is, by setting up an asynchronous Lambda, and this Lambda is in the real sense of the Lambda expression of JavaScript. So an actual Lambda expression with the async modifier expresses the overall AWS Lambda function. And as you can see, most of the computation performed in here are constant computations. You see, did you notice that? There are, if you look at the code, there is only one variable, this one. And by variable, I mean a variable in the JavaScript sense. Variable doesn't mean variable identifier. Variables means a variable identifier that supports assignment. So the var keyword introduces variable identifiers that you can modify and reassign. Actually, perhaps you doesn't know this. Perhaps you don't know this. The term variable originally had this meaning in the past. A variable is an identifier that can be changed. That's why it is called variable. È variabile, è cambiabile. Actually, then the name became a general name for intending variable identifiers in programming languages. But for example, in languages where you cannot modify variables, for example, in functional languages that do not support assignment, even in those languages, we call variables those that you introduce with the let construct, which in JavaScript is the const construct. Writing let or writing const is the same. You write let in most functional languages. In JavaScript, you write const. It is a let binding, basically. And so variable is a general term, but actually we distinguish between variable identifiers that actually are constants and variable identifiers that are truly modifiable. Please don't confuse constants with literals. Most programmers confuse constants with literals. Constant does not mean it has to be a literal. Constant could be even a complex expression or even a complex computation returning one value that you cannot modify. That's a constant. 200, for example, here, 200 is an integer value, and that's a literal constant, which is only an integer value. But I could bind, for example, a record, which is not literal, or I could bind a computation, look here, to a constant identifier. So do not confuse literals with constants. For constants, we mean not modifiable variable identifiers. And even without understanding a word of this code, we don't need to. I'm telling you that this code performs the resizing of an image for, it's a demo, actually, it's an example. And it picks the source image from the bucket, and it uploads the resized image to the bucket. So the bucket is a temporary memory where you can pick things and exchange things with other lambdas. It is a heap memory. It is a volatile memory implementing the heap model. What is the heap model? The heap model means that you bind addresses to objects, to values, and then you bind the names to addresses, and when the program ends, the heap flies away and is deleted. This is the heap model. Please do not confuse the heap as a data structure with the heap in terms of the volatile memory of modern programming languages. They are two different things. And so in this program, you see that the programmer expressed the resizing algorithm for an image in a stateless way. This is very interesting. It means that it doesn't perform global modification of data, only local modifications of data. And actually, it even performs no local modification of data. Even if it defines some var identifiers, actually, these var identifiers only host promises. What are promises? I'm gonna explain what promises are in a few minutes, because promises are an important part of modern stateless concurrent programming, and they are a device, a programming, a coding technique somehow for representing future computations. By the way, does any one of you know how promises work? Promises or future computations, there are two synonyms. Do you know what they are? Or
Yep.
You know them? Okay, Ricardo
Yes.
knows, Lorenzo knows, Alberto knows, perfect. And so you know that promises introduces a paradigm for writing code, because when you have a promise, you don't have the actual object. You only have a box where the result is expected to be inside, but it will be populated afterwards. So you get the box, but not the content, until the content is not computed. And so it's a promise in this sense. And programming in this way is very different from programming in the normal way. I don't know if you have ever programmed with promises or future computations, but the code that you write is very, very complicated with respect to normal code that do not deal with promises. Later on, we will have a few examples. Here we have an example of another example of a Lambda in the sense of an AWS Lambda, but written in Java. In Java, given that the language is a strong typed language with a compiler, unlike JavaScript, which is dynamically typed, in Java, there is more bloat code. Do you know what bloat code is? Bloat code means code that actually does nothing from an algorithmic point of view, but it is just infrastructural syntax. And so you have a lot of interfaces, classes, subclasses, and types for representing operations and data. And this makes the code more verbose, of course, but it also has its own advantages. As you know, statically typed languages have an advantage over dynamically typed languages in terms of writing big programs. When you write big applications, you would prefer a statically typed languages, because you do not have to test all the features. When you write a small program, you might prefer a dynamically typed language for the quickness of its scriptness flavor. So this example shows you how in Java you can implement a handler for an AWS Lambda. What is a handler? A handler is a general term in computer science. Perhaps you already know the term. A handler is a general term for something that stands for something else. Handler means manilla in English. And the term handler is used by many operating systems, for example, for expressing file descriptors. For example, when you open a file, you get the handler to the file, which is a synonym of the file descriptor. Actually, Unix calls file descriptor the identifier that identifies the file in the file system, while Windows, for example, calls handler the entity, the object that you get when you open a file. Why the name handler? Because when you open a file, you don't really have the file, you just have a handler for it. Non hai la cosa vera, hai una maniglia che ti permette di usare la cosa vera. This is the meaning of handler in general, and in this sense, in AWS Lambda, a handler is a handler stream, which is something that represents the stream of the data flow, basically, the stream of data through all the group of your lambdas. Why I'm talking in plural? Because when you write a program using AWS Lambda, you would probably not write only one Lambda, but you would write a number of Lambdas, and you also might write a number of Lambdas that call the other Lambdas. Like when you program in the normal way with normal programming languages, you write your own functions, and then sometimes you also write your own wrappers that call a number of other lower level functions. It is perfectly normal, no, to have an application code which is divided into different layers, and the lowest layers have the primitives, which are a collection of functions, and then you have the mid-level layers that are a collection of functions that call the primitive. You can do the same with AWS Lambda. You can design a number of Lambdas that perform the real computation, the real transformations, and then you design another group of Lambdas that simply call the others in the correct order, like a workflow, basically. And in Java, they express this workflow by means of a handler to the stream of data flow that goes through this workflow. Because basically, if you think at stateless computations, then you can easily realize that if you do not have side effects, because they are only stateless computation, then it means that anything you do is a transformation of data. Since you cannot modify data, because you don't have the assignment, basically, then it means that all you can do is picking an input and producing an output. So I'm talking in very high level. So it means that your program is a connection, is a series of small blocks who get an input, produce an output, and forward the output to the input of the next block, like a workflow. And this way of programming, which is actually the way you program when you write functional code, you transform data into data, and you represent inputs and outputs through types. And so basically, in the end, everything is just a type transformation from a type A to a type B, going through a number of intermediate steps, each of which has its own type representation. So you understand how this is a different way of writing code compared to the way we are accustomed to. Every algorithm we want to express must be expressed into little pieces that transform one step to the other and represent the input and the output, the type of the input and the type of the output. And then we build a chain of these small blocks, and we transform the first input to the last output. And we can call the overall chain another lambda that picks the big input and returns the big output. And inside, it calls the different steps of the lower level chain. This is a stream. It is a stream of data where each step changes its type. Do you understand this? And so you have somehow to abandon your old preconcepts of coding as a stateful machine, modifying memory and modifying variables. In this way, we do not program like this. We have to express the program in a different way, like a sequence of type transformations, which means data transformation. So the workflow is the control flow, which is equivalent to the data flow. This is a very important thing. When you have a program written in an imperative language, usually the control flow is different from the data flow, because the control flow is the sequence of statements of your code. Perhaps you have a while loop, then you have a for, then you have an assignment, then you have an if, then you have an else. So you have a sequence of either loops or iterative constructs and the function calls. This is the control flow, while the data flow is what you get as input and what you put as output. In an imperative language, the control flow and the data flow might be very distinct. In a functional language, but not only in a functional language, in a stateless paradigm, because we are not even talking about functional languages, we are talking about imperative languages used as functional languages, in this case, in a functional way, that is without side effects. So you don't have the for, you don't have the while, you don't have a way for modifying stuff. You only have you can only call other stuff, and you have the condition, the if then else, and you can call other stuff. And so since you cannot modify stuff, you can only call other stuff, then every algorithm is split into small pieces that are a huge series of calls. And so, given that there are a lot of calls, it means that the data flow reflects perfectly the control flow. This is a unification of data flow and control flow. What is the benefit of this? The benefit of this is that we can write code analyzers that verify the data flow, and if the data flow is correct, then the control flow is correct, which is something that you cannot do in normal imperative languages. So Amazon created this big infrastructure that resemble stateless functional programming. Why? Because they also wanted to analyze the correctness and the security of your lambdas, because they host the code of the whole world, because they host it in their servers and they run it in their servers, and they can run analysis, code analyzers. And if their infrastructures unifies control flow with data flow, just by typing the data flow, they can get information about the correctness of the control flow, which is something that you cannot do normally, thanks to the unification. So they can run analyzers and verify that all the lambdas that a given user is performing are correct, or are secure, or are robust, or will scale with different sizes of data. And not only, they can also predict what will happen. If they can analyze in a sound way the data flow, hence the control flow, they can also know by means of the analyzer if the data flow will become big or small. And so they can predict if your lambda will need to be run on a big cluster of computer or on a small cluster of computer, depending on the size of the data flow. If you are transforming 1 million images into another 1 million images, each one on one, then they know that by analyzing the data flow. And so they can say, well, Alvise needs to transform 1 million images. Well, it is better to run his lambdas on a big cluster, very powerful farm of CPUs. If my AWS Lambda performs a computation like resizing an image only on 2 images, they know that by analyzing the data flow and statically, and then they say, well, we can instantiate the executor in a small CPU or in a small computer. Of course, they have a huge cluster of computers. But what I mean is that they can fine-tune the CPU quotas assigned to each step of each flow, and they can predict it. By predicting, they can optimize the overall behavior and performance of the overall server farm. I mean, this has a number of advantages. And it is also important that a big giant like Amazon started to promote this kind of clean programming methodology. It is a methodology of programming that allows the host to reason on programs, to understand the properties of programs, the security properties, the robustness properties, the scalability properties. They can predict what the program do. If instead they had left normal imperative code in the normal way, not encapsulated into small stateless Lambda functions, but if they would have allowed the programmers to write any kind of stuff boxed within one container, they would not be able to predict the behavior of that. Because as you surely know, there's the halting problem. Am I saying that the stateless functional approach allows to break the halting problem? Of course not. Of course not. But still, it has more advantages. Because with static analyzer, you can gain more terrain. You can understand more things compared to imperative code. So it has an advantage. It is not perfect, it is not everything, but it is better than nothing. Well, this is just a series of an example of the API that the programmer has for interacting with the handler and with the context, because you have a context within your handler, and the context is just an object that you can call methods on, and you can have all the name, what is the name, what is the version, what is the limit, what is the group name, etc. You can assess your lambdas, that is the lambdas you have deployed on the AWS servers, from within the code. And from the code, you can interrogate, you can query the system, and you can have a map not in the cartographical sense, but a map in the data structure sense, that is like a hash map, a map in the sense of an associative binary array, I mean, a map in that sense, binding names to properties. Here is another example, but in my opinion, it is not very interesting. Let me show you this as the last thing. This is very interesting. I will share it with you. This is interesting. This is another diagram showing you how the whole thing works by examples. Look, for example, here, the first example is AWS Lambda example showing media transformation. Media transformation means, for example, transforming a picture, like in the example I said before, resizing a picture, or even something more complex, like, for example, compressing a movie, or analyzing an audio, or something like that. And in this diagram, we see a very high level diagram. The user, using the API gateway, actually calls the AWS Lambda, which assesses the bucket. And then the users can go to the bucket and retrieve the result. That's why the Lambda picks the input from the bucket and saves also the output on the bucket, because the user can then go to the bucket, pick the bucket, and pick the output produced by the Lambda. So the bucket is the metaphor for your collection of input and output data. And you can even exchange that. I mean that you can put something in the bucket, use it as an input for a Lambda. The Lambda produces an output on the bucket. You pick the output from the bucket and use it as input for another Lambda, or you combine it with another input, or you can just pick the output and display the result. I mean, you can do anything. It is a general metaphor that can truly adapt to any case. This is an interesting list of advantages of Lambdas. In the last few minutes before the questions, I'm gonna read and explain those for you. When you are redesigning your website or app, you don't need to resize your entire image archive. Transformation on the go gives you high agility. What does it mean? It means that Lambdas are granulari. They perform small tasks split in different Lambdas. Then, as I told you before, you can write other Lambdas that wrap multiple Lambdas. But anyway, you still have the lower levelest primitives. And so, in the case you have to, for example, transform a whole archive of images into something else through some media transformation process. In this case, when you are redesigning your application, and it is something that happens very often, that you have to rewrite or refactor an application, then you do not need to resize the whole archive. You can only resize few of them on demand. It is an on-demand synonym. With on-demand image resizing, just like what I said 1 second ago, you are not required to store your archive in every possible format. Along with this, you can also delete the expired and older images. Why this? Because when you resize, you can throw things away from the bucket. There's a garbage collector going on somehow, and cleaning up unused stuff. It doesn't mean that you are losing anything. Why? Because when you reason in a stateless way, you don't store things. You only transform things. Let me make a better example. Imagine that you have a movie streaming service like Netflix. Okay, so you host a number of movies in somewhere. Then you need to convert all your movies from a AVI format to QuickTime format. It's a stupid example. It has no sense, but it is easy to understand. So the point is to convert everything in order to make people, in the end, access only movies in the QuickTime format. Maybe we can say, maybe because there are no AVI players around, the QuickTime format is the only available in the future, for example, so we want to migrate all our movies from AVI to QuickTime, okay? Then, in a normal architecture, you would need to implement a small script that performs all the transformation in the background while the service is up, perhaps. And until all the transformations are done, you cannot truly deliver the service. And so you have to stop the service. And you also have to save all the transformed movies in the new format, the new QuickTime format, into somewhere else. With the Lambda approach, you do not have to think of this in this way. You just have to think in the following way. I have movies. the survey is, given the name of the movie, I want the stream of the pixels. That's the service. And when I want to convert all the movies in a different format, it is a problem of the inner data flow. It is not seen from the outside. It is not a problem for the user. It is a problem of internal data flow, where, well, you can introduce a new Lambda inside the data, the workflow. Inside, you insert a new Lambda that converts an AVI to a QuickTime, and every time it is needed on demand, it will be executed, even in parallel, even in different clusters, because everything scales automatically and for free. And so you don't even save the results. You don't need to have to store the new movies in the new format. You don't think about that. You only have names and convert names into names by a system of caches and buckets and garbage collector, which is automatic. You simply will keep the converted movies once you already have converted them. And if you still have to convert one because no user has seen that specific movie for 1 year, well, the first user that will ask for streaming that very movie will automatically make the conversion, and the conversion will stay cached. So I'm not saying that this is something that you cannot do in another way. Of course you can. Clever people and expert programmers already built software in this way in the past. For example, Netflix used to do the same on-demand thing without using AWS in the past, because they had intelligent programmers that implemented a system that does every task on demand, only if it's needed, by caching, by collecting, garbage collecting, etc., etc. So they already had the technology to perform things in a clean and on-demand way. The point is that AWS Lambda gives you no alternatives. So with AWS Lambda, you must implement things in this clean and scalable way. So it is not only a methodology, it is also a discipline, una disciplina. So it is almost 7 o'clock. I will share with you a number of links that you might enjoy reading if you want to go into the details of AWS Lambda. What I can suggest for you as young programmers and young computer scientists, I feel I can tell you this suggestion. The future of coding is functional. This is clear because every programming languages introduced functional constructs. Even Amazon introduced a web technology, a super cloud technology based on stateless computation. Functional does not mean Haskell. Functional does not mean F#. Functional means stateless computations through a rigid data flow. This is the meaning of functional. So it doesn't mean that you will program in Haskell. It will mean that you have to understand the principles of functional programming, because all the technology that is coming in the forthcoming years will be based on this approach. Why? For 3 reasons. Because it imposes a discipline, a clean discipline, and this discipline produces more correct programs, but not only. Programs that you can analyze, and programs whose behavior you can descript and predict more precisely. The overall point of software validation as a huge field of computer science is to understand what programs do, in the sense of description of their semantics and the prediction of their semantics. And in order to make program validation and software verification occur more in a higher sense, in a better sense, we needed to change the paradigm, because imperative languages did not allow this. And we are coming from 40 years of imperative coding with programs that we cannot describe. Have you ever noticed that when there's a bug in a program, you have to test it? There is no way for an analyzer or for a compiler to understand that the program will introduce a bug, because programs were traditionally written using the Turing machine metaphor, which is by modifying memory. The new century, the century we are living in now, is introducing a new way of programming that is, of course, equivalent to the Turing machine, but it disables one basic operation, the modification. And in this way, by disabling the modification, we open the door to a number of incredible benefits in terms of predicting and describing what the program does. Because analyzers can understand the behavior and the semantics of a program without assignments much better than understanding a program that performs a lot of assignments. This is a goal, an achievement of static analysis as a branch of computer science that we are all enjoying with these technologies. The prediction of the semantics of programs and the elimination of some bugs, not all, but some bugs, before running it and before testing it. If you have a question, you can ask them to me. Now I will share you the links. I will simply share the links here in the chat. So you copy them. If you're interested, put them on a text file, and then you can study them later, because we are going to lose this window. You just copy and paste them. Actually, some of the last links, as you can see, are different pages of the same documentation. So I'm not going to link you all of them. You just browse through the menu on the left and simply do that in that way. Okay, I already shared that video. Okay, so guys, if you have no questions, we shut down. Just a random question about Lambda. I've made a quick search and I found out that programmers proficient in functional language, especially Clojure, are the richest. Yes. There's a strange thing. I should, for example, I personally should be very rich in this sense, because I am one of the few functional programmers in the world, basically. But I already explained to you why. I spent the last 10 minutes to explain to you why. Because functional languages are better. Simply that. And they are the future. And the world is starting to realize this. Functional specialists already knew that 30 years ago. But the world is slow to understand things. And the world is accepting that imperative languages are worse now. They're accepting it now. The world is becoming functional. Closure is just an example. No, not every company. No, it is a very slow process. If you go around here, Lorenzo, if you go and work in Venice, Treviso, Padova, you're not going to work for illuminated people that understand that the functional approaches, the functional languages is better. They are simply web agencies and small companies that write soft web pages or websites with the technology that simply exists. You don't have to confuse what is the local panorama with the world panorama. The local panorama is obsolete, of course, because we live in Veneto, we live in Treviso, Padova, Venezia. There are no illuminated programmers here, but the overall community of development in the world is slowly migrating to functional world. And in the following years, in the following 10 years, slowly, even the local small companies, like in our territory, will start using what the rest of the world will use, with a slight delay, no? And so in 10 years, if you will be an expert functional programmer, you will have a better salary. You will get more money. Is there any other question? So my suggestion is to study AWS Lambda in particular, because it is very request from companies. And in general, to study more functional languages. In my little own, I try to teach functional programming in all the courses that I do, because functional programming is not anymore just F#. No one cares about F#. Functional programming is a methodology of writing code, and it is widespread to different languages. So I can teach the principles of functional programming even in JavaScript or in Java or in Python. Unfortunately, there is no course in our university. Let me shut down the lesson and we switch to Italian for a second. Let me stop the lesson. The lesson ends here. Thank you for your attention.